Alright guys, so you have with you the Common Final Exam from fall 2017. Alright, so we're going to start with part 1. This is the no calculator part, so our goal here is to make sure that we work through each one of these problems without the use of a calculator. Alright, so in problem number 1, we are given a function f of x equals 2x cubed plus 4 times the natural log of x plus 7, and we would like to evaluate the derivative of this function at x equal to 2. Alright, so let's start by finding the derivative of said function. Alright, so this derivative is not very hard. We don't need any special rules. F prime of x is equal to, so derivative of 2x cubed is equal to 6x squared plus 4 times the derivative of natural log of x is 1 over x. So this will be 4 over x. Derivative of a constant, of course, is 0. Alright, so we want to evaluate at 2. So plug in a 2 for x, so 6 times 2 squared plus 4 over 2 is equal to, let's see, 2 squared is equal to 4 times 6 is equal to 24 plus 4 over 2 is equal to 2. So this is equal to 26. This is answer C. All right, problem number 2. It says let g of x be equal to e raised to the power 2x plus 1, quantity raised to the power 3. We would like to find the derivative of this function and evaluate at 0. Alright, so in order to find the derivative of this function, I'm going to need the chain rule. And in fact, I'm going to need to use the chain rule twice here. So first, let's consider the outside function is something cubed. So the derivative, g prime of x, will be equal to 3 times, leave the inside alone, e to the 2x plus 1, quantity squared. So that's derivative of the outside, times derivative of the inside. Derivative of e to the 2x. Again, derivative of the outside is e to the 2x times derivative of the very inside. Derivative of 2x is equal to 2. And now we would like to evaluate at 0. So g prime evaluated at 0 is equal to 3 times e to the power 2 times 0 plus 1, quantity squared, times e to the power 2 times 0 times 2. Let's see, this is equal to 3 times e raised to the power 0 is equal to 1. So 1 plus 1 squared, so that'll be 2 squared, times, again, e to the power 0 is equal to 1 times 2. This is equal to 3 times 4 times 2, which I get to be equal to 24. Answer D. Number 3 says let h of x be equal to x squared times sine of 4x. We would like to find the derivative h prime of x. All right. For this problem, we're going to need the product rule as well as the chain rule. Here we go. H prime of x will be equal to, so by the product rule, it will be derivative of the first, so derivative of x squared is equal to 2x, derivative of the first times the second, sine of 4x, plus the first, x squared, times derivative of the second, derivative of sine of 4x by the chain rule, derivative of the outside, derivative of sine is equal to cosine, leave the inside alone, 4x, times derivative of the inside, derivative of 4x is equal to 4. Alright, so now we just have to match it with the correct answer. The answers seem to be written, they seem to be written the other way around. So if you want to clean up and write this term first, 4 times x squared times cosine of 4x, plus we can write this term second, 2x times sine of 4x. This then matches answer D. right, number 4. Gives me big F of x is equal to the square root of 4x squared plus 9. We would like to find the derivative f prime of x. So again, a chain rule problem here. We're going to find derivative of the outside times derivative of the inside. So f prime, let's see, big F prime of x is equal to. All right, derivative of a square root. What is the derivative of the square root of x? This is one of the derivatives that we have committed to memory. Now, you can derive it the long way each and every time, but it's really going to be beneficial if you know that the derivative of the square root of x is equal to 1 over 2 times the square root of x. So here, derivative of the outside is 1 over 2 times the square root of x. Leave the inside alone. 4x squared plus 9 times derivative of the inside. So times derivative of 4x squared plus 9 is equal to 8x. All right, we can clean this up just a little bit. So let's see, 8x over 2 times the square root of 4x squared plus 9. 8 over 4 is equal to 4. And so this matches answer B, I believe. Yes, answer B. Number 5. We're given big G of x is equal to the natural log of x squared divided by x squared plus 1. We would like to find G prime evaluated at 1. All right, so we can find the derivative in the form that it is at, but let's quickly see how deep is so this is a composite function. How many levels deep is this composite function? My very outside function is the natural log. To the inside of that, there's a quotient. And then to the inside of that, there's x squared as well as x squared plus 1. Let's clean up our algebra before we do our calculus. This is a natural log that has a quotient, a fraction on the inside. So we can start by saying, all right, g prime of x, I'm not taking a derivative, is equal to the natural log of x squared minus natural log of x squared plus 1. That makes my derivative a little bit easier. All right. In addition to that, if you'd like, you can go ahead and bring this 2 out. You can say that this is 2 times the natural log of x minus the natural log of x squared plus 1. All right, so now I'm ready for that derivative. G prime of x is equal to 2 is a coefficient, hold them over. Derivative of the natural log of x is equal to 1 over x, or you can write 2 over x if you'd like, minus derivative of the natural log of x squared plus 1. By the chain rule, it will be 1 over x squared plus 1, derivative of the outside, times derivative of the inside. If you want to write the 2x on top, that's fine. All right, so now we would like to evaluate at 1. So g prime evaluated at 1 is equal to 2 divided by 1 minus 2 times 1 divided by 1 squared plus 1. This is equal to 2 minus, let's see, 2 over 2 is equal to 1, which means this answer is B. All right, problem number 6. Wants me to find an equation for the tangent line to the graph of f of x equals x squared divided by 2x minus 3 at the point where x is equal to 2. All right, so when we find the equation of a tangent line, well, when you find the equation of any line, we need 2 things. We need the slope of the line, and we need a point that it is passing through. So let's start by finding the slope of the line. This means we're going to need the derivative. So f prime of x is equal to, by the quotient rule, derivative of the top, 2x, times the bottom, 2x minus 3, minus the top, x squared, times derivative of the bottom, which is just equal to 2, all over the bottom squared, all over 2x minus 3, quantity squared. All right, so now the slope of this line is going to be this derivative evaluated at 2. So the slope is equal to f prime evaluated at 2. So I will have 2 times 2 times 2 times 2 minus 3 minus 2 squared times 2 over 2 times 2 minus 3 quantity squared. All right, so let's calculate. We don't have a calculator, but these numbers are not bad. This is equal to, let's see, 2 times 2 is 4 times, let's see, 2 times 2 is 4 minus 1 is equal to 1, minus 2 times 2 is 4 times 2 is 8, over 2 times 2 is 4 minus 3 is 1 squared. 4 minus 8 is equal to minus 4. All right, so that is the slope of my line. I also need a point that this line is passing through. So that means I'm going to, in order to find y naught, I'm going to evaluate the original function at 2. So f evaluated at 2 will be 2 squared divided by 2 times 2 minus 3. That is equal to, let's see, 4 over 1, which is simply just equal to 4. All right, so now we have it. My slope is equal to negative 4. The point that I'm passing through is the point 2 comma 4. Let's plug it into point slope form. So y minus y naught is equal to m times x minus x naught. So that means that y minus 4 is equal to negative 4 times x minus 2. So y is equal to negative 4x plus 8, bring the 4 over, plus 4. So y is equal to negative 4x plus 12. I need to zoom out just a little bit so you guys can see everything that I've done here. All right, so the answer here is going to be, let's see, number 6. Answer here is going to be A, negative 4x plus 12. All right, problem number 7. Gives me a function f of x equals x cubed times e raised to the negative 3x and wants me to find all of the critical numbers. All right, how do we find critical numbers? So the critical numbers AE, the local minimum and maximum points, will occur where the first derivative is equal to 0. So I'm going to start by finding the first derivative, and then we will set it equal to 0, of course. So here we go. F prime of x is equal to, again, by the product rule, this will be derivative of the first, 3x squared, times the second, e to the negative 3x, plus the first, x cubed, times derivative of the second. So derivative of e to the negative 3x by the chain rule is e to the negative 3x, derivative of the outside, times derivative of the inside. Derivative of negative 3x is equal to negative 3. And we're going to set this derivative equal to 0. Let's see, I can factor out of each one of these terms. Since this guy's been set equal to 0, I can factor out a 3, an x squared, and an e to the negative 3x. So when I factor that out, over here I'm left with just 1. Let's see, over here I'm left with an x and a negative, so just minus x. This is equal to 0. All right, so we get to set each one of these terms equal to 0. So we can say 3x squared equal to 0, or e to the negative 3x equal to 0, or 1 minus x equal to 0. All right, so from this term, 3x squared equal to 0, we get that x is equal to 0. All right, so for an exponential function, does an exponential function or a standard exponential function e to the kx, does that ever equal 0? Never does. So here there's no solution. And then finally 1 minus x is equal to 0, so therefore x is equal to 1. All right, so there we have it. Our critical points occur when x is equal to 0 or x is equal to 1. Answer E. All right, problem number 8. On which interval below is the graph of g of x equals x to the power 4 plus 2x cubed minus 36x squared plus 1 concave up? All right, so we know that when we're dealing with concavity, we're dealing with the second derivative. The second derivative of a function tells me about the concavity of that function. So let's start by finding the second derivative. The first derivative, g prime of x, is equal to 4x cubed plus 6x squared minus 72x. The second derivative, g double prime of x, is equal to 12x squared plus 12x minus 72. And we want to set that second derivative equal to 0 to solve. So you can see that a 12 will factor out of this equation. If you factor out a 12, you'll have x squared plus x minus 6, right? So if you factor out the 12, this guy will factor into x plus 3, x minus 2. All right, and then we get to set each factor equal to 0. So I will set x plus 3 equal to 0, which means x is equal to negative 3. Or I will set x minus 2 equal to 0, which means that x is equal to 2. So now, before we declare victory, we need to go ahead and test and see, do I really change concavity at each one of these points before we decide that they are in fact inflection points? And if so, how does that concavity change? So like I said, I like the little number line method, so I'm going to construct a little number line over here, and I will plot these 2 points, negative 3 and 2. Those are my possible inflection points. So I would like to test a test value from each one of these intervals that I'm going to plug back into the second derivative just to see, does it make the second derivative positive or negative. So I'm going to use, on this interval, I will use negative 4 as a test value. I will use 0 as a test value on this interval, and I will choose 3 as a test value on this last interval. So if I plug those into the second derivative, so f double prime of negative 4 is equal to, all right, so back into this second derivative, we plug it. Okay, so negative 4 squared is going to be a positive number, so this will be 12 times 16 plus 12 times negative 4, so that'll be minus, let's see, 48 minus 72 gives me positive 72. All right. The second derivative evaluated at 0, that one will be a little bit easier, right? If we evaluate at 0, that's equal to minus 72. And finally, the second derivative evaluated at 3. All right, so 12 times 3 squared, so 12 times 9 is equal to 84, right? Plus 12 times 3, so plus 36 minus 72, I get is equal to positive 72. All right, so we don't care about the values as much as just the signs. I can see that on this interval, the second derivative is positive, then it is negative, then it is positive again. All right, so that means I'm concave up, concave down, concave up. So which one of these guys matches one of my intervals where I am concave up? Am I concave up on the interval negative 2 to 3? Nope. Negative infinity to 2? Negative infinity to 3 would work, right? So no. 2 to infinity? Well, yes, in fact, from 2 to infinity, I am concave up. So C definitely is an option. C is my answer. Let's check the other ones. Negative 3 to 2, I'm concave down, and 1 to infinity is not even an option. All right, so answer here is C. All right, problem number 9. wants me to evaluate the limit as x approaches 2 of x squared plus 7x minus 18 divided by x minus 2. All right, so if we plug in this number 2, we will get 4 plus 14 minus 18 is equal to 0 over 0. All right, so when it comes to limits, when you see 0 over 0, 0 over 0, of course, is not equal to 1. It's not equal to 0. It's an indeterminate form. It tells me that I need to go do something else. I need to clean up, factor, cancel out, possibly use L'Hopital's rule, right? So this problem is perfect for L'Hopital's rule. You can use L'Hopital's rule if you want. I'm going to do this problem by factoring. So I am identifying here that this is equivalent to the limit as x approaches 2. X squared plus 7x minus 18 will factor into x plus 9 times x minus 2 divided by x minus 2. All right, so we see that we have these two terms that can then cancel out. The x minus 2 terms cancel out with each other, and we are left with the limit as x approaches 2 of x plus 9. At this point, we can evaluate, right? That's the first rule of limits. How do we find the limit? We plug in. So if we plug in right now, 2 plus 9 is equal to 11. Answer here is D. Problem number 10. Again, we have a limit here. This time the limit as x goes to infinity of 5 minus 4 times x divided by x squared plus 5x minus 6. All right, so there's a variety of ways that we taught you guys that you can approach this problem. First of all, again, what you need to identify is that if you plug infinity in here, you're going to get negative infinity divided by infinity. All right, so that's one of my indeterminate forms. It's negative infinity over infinity. So again, here we know that there's something more that we need to do. All right, so the first thing that you see is that since this is a polynomial divided by a polynomial, right, it's a rational expression, and we're finding the limit as x approaches infinity, we had some rules. We said if the degree of the top and the degree of the bottom are the same, this limit will go to the ratio of the leading coefficients. If the degree of the bottom is bigger than the degree of the top, it'll go to 1 over infinity, which essentially is equal to 0. If the degree of the top is bigger, it will go to positive or negative infinity. And you're welcome to use one of those shortcut rules on the multiple choice part of the test. Right? We also had a more sort of inclusive way. We would multiply both the numerator and the denominator by 1 over x raised to whatever power we see in the denominator. So you could multiply both numerator and denominator by 1 over x squared, clean that up. But I think the easiest way to approach this problem is by using L'Hopital's rule. So that's how I'm going to do it, the easy way, right? So by L'Hopital's, this limit is equal to the limit as x go to infinity. So the derivative of the top, derivative of 5 minus 4x is equal to minus 4. The derivative of the bottom is equal to 2x plus 5. So again, we try to take the limit again. If I try to take the limit again, I get negative 4 over infinity. Anytime you have a constant divided by infinity, we know that that is always 0. Answer here is C. All right, number 11 says, let y be equal to x squared plus 3x plus 1. Let's evaluate the differential dy when x is equal to 4 and dx is equal to 0.2. All right, so what is a differential? A differential is the following. So a derivative, if we use Leibniz notation, a derivative is dy dx. The derivative of y with respect to x here will be equal to 2x plus 3. You guys agree? So a differential means I'm just going to take this little dx and multiply it over to the other side. So a differential is dy equals 2x plus 3 times dx. That is a differential. And now we just get to plug in. They give us some values, so let's plug and chug. So the differential dy will be equal to 2 times x is equal to 4 plus 3 times dx, which is equal to 0.2. Again, shucks, we don't have a calculator. That's okay. We can calculate this. 2 times 4 is 8 plus 3 is 11 times 0.2. So let's see, 11 times 2 is 22. Move the decimal place back 1. This is equal to 2.2. Answer B. All right, number 12. It says find the general antiderivative of g of x, which is equal to 4 over x plus 2 times cosine of x. So the general antiderivative means we're integrating this function, right? So big G of x will be equal to, all right, so 4 is a coefficient that we're going to hold over. What is the antiderivative of 1 over x? Natural log of the absolute value of x, right? So just hold that 4 over. He's a coefficient. The antiderivative of 1 over x is the natural log of the absolute value of x. All right, next up, again, 2 is a coefficient. Just hold him over. The antiderivative of cosine of x. What did I take a derivative of to get positive cosine of x? Positive sine of x. So this will be plus 2 sine of x. And then do not forget, on any general antiderivative, we put a plus c at the end. So plus c. Answer here is C. And one more. Number 13 wants me to use, specifically they indicate to me, they give me a hint here, use L'Hopital's rule to evaluate the limit as x approaches 1 of 2 times the natural log of x divided by x minus 1. So just because I'm skeptical, I'm going to double check. If I were to just simply plug 1 in here, natural log evaluated at 1 is equal to 0. If I plug a 1 in here, 1 minus 1 is equal to 0. Make sure that you have a limit in the form 0 over 0 or infinity over infinity before you apply L'Hopital's rule. So this basically is your permission slip. Sure, we may now go ahead with L'Hopital's. So this will be equal to the limit as x approaches 1 of, let's see, again, 2 is just a coefficient, hold them over. The derivative of the natural log of x is equal to 1 over x. So I get 2 over x divided by the derivative of x minus 1 is just equal to 1. Again, plug in the limit and see what you get. So if we plug in here, 2 over 1 is equal to 2. Answer is D. All right, let's see. We started this version at 9:15. It is now, let's say, 9:45. So with going over these problems thoroughly, I have written down every step and talked through it. It has taken us 30 minutes. So the reason I'm pointing this out to you is to let you guys know you have plenty of time, right? You don't have to rush through this. If you know what you're doing, you have more than ample time to complete this, okay? So you have time to go back over, make sure that you didn't make a careless error somewhere, that you didn't mess something up, all right? All right, any questions? You guys have not asked a single question. Any questions on this part 1 of the exam that we've gone over? Good? Was it bad? It's not that bad, right? All right, here you go. Part 2 of the exam. So we will assume that you are allowed to use your calculator on any of these problems that follows. So if it is 3:30 in the afternoon and you're starting to complete part 2 of the exam and you don't have your calculator yet and you get to a problem that really requires a calculator, just skip it, move to the next problem. The majority of problems you will be able to solve without a calculator on parts 2 and 3. All right, so problem number 1 says, suppose that f is a differentiable function with the following table of values. And so they provide us some values for f of x and f prime of x. We would like to find g prime of 2, given that g of x is equal to f of x quantity cubed. All right, so I'm going to start up here. Just going to write down g of x is equal to f of x quantity cubed. This is a composite function. My outside function is something cubed. My inside function is f of x. So that means that this derivative is going to require the chain rule. All right, so g prime of x will be equal to, derivative of the outside is 3 times f of x quantity squared, times derivative of the inside is just f prime of x. Now we would like to evaluate this at 2, so g prime evaluated at 2 is equal to 3 times f of 2 squared times f prime of 2. Oops, don't even need a parenthesis there. All right, and let's go to our table of values. All right, what is the value of f of 2? F evaluated at 2 is equal to 1. So this is equal to 3 times 1 squared. The value of f prime of 2, f prime evaluated at 2 is equal to 3. So this is equal to 3 times 3, which is equal to 9. Answer is E. All right, problem number 2 kind of touches on something that we went over in class, I would say kind of fast. This was part of a review that we did. The problem wants to know which of the following functions are one-to-one. So I want to just quickly remind you guys of the definition of what is a one-to-one function. So definition. By definition, one-to-one means that it is a function where each y value corresponds to, every y value corresponds to exactly one x value. So if you put your finger anywhere on the graph, right, and you consider that particular y value, there's only one value of x that will map to that y, right? That is what a one-to-one function is. We usually can do this really easily by using the horizontal line test. So we use the horizontal line test. So here we go. I'm given 3 functions and I'm asked for each one of them if it is a one-to-one function. So let's start with sine of x. So if I graph sine of x, I'm going to just jot a small little graph here. You guys know that sine of x looks like this, right? Here's sine of x. And so I can construct, I'll do it with a different color, I can construct a horizontal line that crosses this function more than once. Therefore, it fails the horizontal line test. This guy is not one-to-one. Right? So this guy is not one-to-one. All right, the second guy, g of x is equal to x squared. All right, we know that x squared looks like this, right? It's a parabola. And sure enough, again, I can construct a horizontal line that intersects this graph more than once. So this guy is not one-to-one. All right, finally, 2x plus 1 is a line. It's going to be a straight line that looks like this, right? Here's 2x plus 1. There's no way that you can construct a horizontal line that will intersect that graph more than once. So this guy is, you can say here, check. This guy is one-to-one. Very good. So the answer here is going to be, the only guy that is one-to-one is 3. So my answer is C, 3 only. All right, problem number 3 is giving us a function f of x is equal to the square root of x plus 1 minus 2, and wants me to find the inverse of this function. All right, so the first thing that we have to do is ensure that the function is in fact an invertible function. You can quickly graph it on your calculator and make sure that it is a one-to-one function. If a function is not one-to-one, then we cannot find its inverse. All right, so I checked. This is a one-to-one function. So the first thing that we do is, instead of the f of x notation, I'm going to write this as y equals the square root of x plus 1 minus 2. And so immediately the whole purpose of an inverse function is that we switch x and y values, right? So go ahead and switch your x and y values. So that means the inverse function will be the function x equals the square root of y plus 1 minus 2. And of course now we need to solve for y. Alright, so I will start by adding 2 to each side. So I will have x plus 2 is equal to the square root of y plus 1. We can kill off the square root by squaring both sides. So x plus 2 quantity squared is equal to y plus 1. And then finally, to get y by itself, subtract 1 from each side. So x plus 2 quantity squared minus 1 is equal to y, which of course is equal to the inverse function. So this is answer number B. Answer B. All right, problem number 4. Suppose that f prime of x is equal to 3 over x plus 2x, and that f of 1 is equal to 3. We would like to find a formula for f of x and then evaluate at 2. All right, so we're being provided with f prime, and we are looking to find the function f. So that means we need to find the antiderivative, or the integral here. So I'm going to start by finding f of x. Here is equal to. All right, again, 3 is a coefficient. Hold them over. The antiderivative of 1 over x is equal to natural log of the absolute value of x, plus, by the power rule, 2x. If I add 1 to the exponent and divide by the new exponent, it is equal to 2x squared over 2. The 2's here will cancel out. And then, as usual, we always add a plus c to a general antiderivative. All right, but now this problem tells me that f of 1 is equal to 3. I'm being given a boundary condition in order to calculate c. All right, so f of 1 is equal to 3 times the natural log of 1 plus 1 squared plus c, and together this is equal to 3. All right, so 3 times, let's see, the natural log of 1 is equal to 0, right? So this whole term is equal to 0. So I get that 1 plus c is equal to 3. Subtract 1 from both sides, I get that c is equal to 2. So that means that my function f of x is equal to 3 times the natural log of the absolute value of x plus x squared plus 2. That is f of x. So now we need to evaluate f of x at 2. F of 2 is equal to 3 times the natural log of 2 plus 2 squared plus 2. This definitely is a calculator problem. You can break out your calculator and punch that in. I get a value here of 8.079. This rounds to 8.08, which is answer B. All right, so in problem number 5, we are given a piecewise function, f of x equals kx minus 2 for all x not equal to 3, equal to k when x is equal to 3. And we're being asked, determine the value of k that makes this function continuous at 3. All right, so for a function to be continuous, definition of continuity is that the limit exists, that the function is defined at that particular point, and that those two things are equal. All right? So what we're going to have to do to ensure continuity is we're going to say that the limit has to exist here. So that means, let's say, the limit as x approaches 3 of this function f of x. So the limit as x approaches 3. So this means x is not 3, is going to be kx minus 2. Has to be equal to the function value when x is equal to 3. So that has to equal k, right? All right, so is there anything in this limit that stops me from just the simple way of evaluation, just simply plugging it in? Not really. So k times 3 minus 2 is equal to k. All right. So let's see. I will have 3k. I'm going to take the negative 2 to the other side and subtract k over here. So 3k minus k is equal to 2. So this means 2k is equal to 2, which means k is equal to 1. And you can test that. If we plug 1 in for k, then at 3 this function will have the exact same values. Answer here is B. All right, problem number 6. F of x here again is a piecewise function. I have x plus 2 for all x less than 0. I have x squared minus 1 for all x on the interval between 0 and 2. And the function is equal to 4 minus x for all x greater or equal to 2. We would like to find the limit as x approaches 2 from the right-hand side. All right, so you need to consider if you're approaching 2 from the right-hand side. So think about a number line. Where are you at? If you're approaching 2 from the right-hand side, that means you are at a number bigger than 2, right? You are on the interval x greater or equal to 2. Right. So we will use this equation to plug in. So this is equal to the limit as x approaches 2 of 4 minus x. We can simply just evaluate. This is equal to 4 minus 2, which is equal to 2. Answer B. Is there a question? Yes. For question 5? Yeah, so the question on number 5 was, what does k have to be to ensure continuity? So we go back to the definition of continuity. So we said if it was a limit from the left and a limit from the right situation, we would set those two equal. We would say the limit from the left must equal to the limit from the right. You can go ahead and plug in whatever that limit is for x, and that should leave k as your only variable. Yes? Exactly. The second one, there's no k. We just simply want to find the limit. We just want to know what the limit is. So for a piecewise function, we just have to determine which one of the equations we are working with. So since the limit here, we're approaching 2 from the right-hand side. If you think about a number line, if you are on the right-hand side of 2, that means you are on the interval x greater or equal to 2. And so therefore we use the equation 4 minus x. Question. Okay. All right, so the next problem is a pain. Oh my goodness. I don't know why. Evaluate the limit as h approaches 0 of a plus h cubed minus a cubed divided by h. Now, I know I've taught college algebra, I've taken college algebra, I've talked to you guys about it. I know you guys know this, but how many of you guys actually remember the formula for a binomial cubed? All right, so we have to, okay, so that, I don't remember it either, okay? There is a formula. If you have a plus b quantity cubed, there's a formula that tells us exactly what that is. And if you know what that formula is, good for you, really. You're going to do really well in this exam. So for the rest of us, I don't know what a plus h quantity cubed is. So before I even start this problem, let's quickly get that out of the way. All right, here we go. I'll come back to this problem. All I'm doing right now is, what is a plus h quantity cubed? It is equal to a plus h times a plus h quantity squared, yes? This is equal to a plus h times. All right, what is a plus h squared? It is equal to a squared plus 2ah plus h squared. And now we get to distribute this term in here. So I'm going to take the a and multiply everything in here with the a first. So that'll be a cubed plus 2a squared times h plus h squared times a plus, now I'm going to multiply everything by the h. So this will be a squared times h plus 2ah squared plus h cubed. You guys agree so far? I just distributed that term on the outside. And now we have to clean it up. Combine like terms. So this is equal to a cubed. Let's see. I have the terms that contain the a squared times h. There's two of them here, and there's one of them here. So this will be plus 3 times a squared plus h. And so then I have the terms that contain the h squared times a. There's one of them here, and there's two of them here. So this will be plus 3 times a h squared, and then finally plus h cubed. Okay. So that took an extra minute. Sometimes there will be problems like these. That's going to take an extra minute. That's okay. All right, so let's return to the problem. We would like to evaluate the limit as h approaches 0 of a plus h quantity cubed minus a cubed divided by h. So this limit will be equal to the limit as h approaches 0 of. All right, so we're expanding. So the a plus h cubed, there it is. It is a cubed plus 3a squared times h plus 3a times h squared plus h cubed minus a cubed divided by h. Let's see, what cancels out? I have an a cubed and an a cubed that cancels out. So if you look at every term that is left, then every term contains an h. So we can factor out an h. So I can factor out an h, so I'll be left with 3a squared plus 3ah plus h squared divided by h. And so now the h's cancel, right? So we are left with the limit as h approaches 0 of 3a squared plus 3ah plus h squared. And at this point, we can actually evaluate that limit. So if you plug in a 0 for h, this term goes to 0, this term goes to 0, and we are simply left with 3a squared. Answer here is E. All right, questions here on this problem? Yes? Could have done that, yes. Yeah, if you knew the definition of the derivative, absolutely. All right. Problem number 8. It says find the linear approximation of the function f of x equals x over 2x minus 1 at the point a equal to 1. All right, so linear approximation really is, I mean, it's almost the same thing. This problem might as well have said find the equation of the tangent line at x equal to 1. All right, so linear approximation, I will remind you guys, we have a formula, and that formula is L of x is equal to f of a plus f prime of a times x minus a. That is our formula. So we need to know, we already know a, that's given in the problem, but I need to find f of a and f prime of a. All right, so here we go. The derivative of this function with respect to x, I'm going to need to use the quotient rule here. Derivative of the top is equal to 1 times the bottom is 2x minus 1 minus the top is equal to x times derivative of the bottom is equal to 2. All over the bottom squared. So all over 2x minus 1 quantity squared. Now we're going to evaluate at 1. So f prime evaluated at 1 is equal to 2 times 1 minus 1 minus 1 times 2 divided by 2 times 1 minus 1 quantity squared. This is equal to, let's see, 2 minus 1 is equal to 2 minus 2 over, let's see, 2 minus 1 is equal to 1. 2 minus 2, however, is equal to 0. Hold up, did I mess it up? 2 minus 1 is equal to 1, not 2. Sorry. Sorry, this is equal to 1. I surely did write that wrong. All right. So 1 minus 2, I get an answer then here of negative 1. All right. I also need to know what the original function will be evaluated at 1. So that'll be 1 divided by 2 times 1 minus 1. So let's see, this will be 1 over 1, which is just equal to 1. All right, so now I have all the information that I need. I can go ahead and plug it into my formula. So L of x is equal to f of a, so f evaluated at 1 is equal to 1, plus f prime of a, the derivative evaluated at 1, is equal to negative 1, times x minus a, of course a is equal to 1. Clean this up just a little bit. L of x is equal to 1. Let's see, this will be minus x plus 1, so I get that this is equal to negative x plus 2. It is equal to negative x plus 2. Answer is A. Number 9. Suppose that we have the equation x cubed times y squared plus 2x minus y equal to 4. Let's find the derivative dy dx and evaluate it at the point 1, 2. Alright, so I'm going to have to find the derivative here implicitly because there's no way for me to solve for y. So by implicit differentiation, I'm going to start by using the product rule here. I have x cubed times y squared. So by the product rule, derivative of the first, derivative of x cubed is equal to 3x squared. So derivative of the first times the second plus the first x cubed times derivative of the second. Derivative of y squared is equal to 2y. But because I just took a derivative of a term containing a y, I'm going to tag on a dy dx. All right, plus derivative of 2x is equal to 2 minus derivative of y is equal to 1 times dy dx equal to, and of course derivative of a constant 4 is equal to 0. So it doesn't matter. You can either bring all of your terms that contain dy dx to the right hand side or leave them on the left hand side. It doesn't make a bit of difference because we're evaluating this derivative anyway. So I'm going to say that these guys, I have this term and I have this term that contain the dy dx. I will leave them on the left hand side. I'm going to move all the terms that do not contain the dy dx. I'm going to move them to the right hand side of the equation. So I have x cubed times 2y times dy dx minus dy dx equal to minus 3x squared y squared minus 2. So on the left hand side, let's factor out that dy dx. So I'll be left with x cubed times 2y minus 1 equal to negative 3x squared y squared minus 2. And so the last thing that I do to get dy dx by itself is to divide each side by this residual term. So I get that dy dx is equal to negative 3x squared times y squared minus 2 divided by x cubed times 2y minus 1. Right? Now we need to evaluate this derivative at the point 1, 2. So dy dx evaluated at 1, 2 is equal to negative 3 times 1 squared times 2 squared minus 2 all over 1 cubed times 2 times 2 minus 1. Let's see, when I evaluate, when I clean up, I get here in the top, I get minus 14 divided by 3, which actually is one of the answers that is listed. Answer C. All right, problem number 10. We're given a function f of x equals x to the power 5 minus k times x to the power 4 plus 2x plus 1 for some random constant k, right? So the problem tells us that f has an inflection point at 3. What is k? So what do we know about inflection points? I know that if I find the second derivative and set it equal to 0, that gives me the inflection point. So if I find the second derivative here, and I plug in x equal to 3, then that should be an inflection point. Set that equal to 0, and that should be an inflection point, right? So let's start by finding that second derivative. So first derivative, f prime of x, is equal to 5x to the power 4 minus 4 times kx cubed plus 2. The second derivative, f double prime of x, is equal to 20x cubed minus 3 times 4 is 12 times kx squared. And we are going to, in order to find k, we're going to evaluate this derivative at 3. So 20 times 3 cubed minus 12 times k times 3 squared must be equal to 0. All right, so when I evaluate 20 times 3 cubed is equal to 540 minus, let's see, 3 squared times 12 is equal to 108 times k is equal to 0. So of course this gives me that 108k is equal to 540, which means k is equal to 540 divided by 108. This reduces to 5. Answer here is E. All right, problem number 11 says we wish to solve x cubed plus 4 equal to 4 using Newton's method. We would like to use x sub 1 equal to 1 as our initial approximation and then find the second approximation x sub 2. So we're not asked for the exact solution, but for x sub 2 in this particular case. All right, so what I'm going to go ahead and do here is, first of all, in order to use Newton's method, I need an equation that has been set equal to 0. So I will have x cubed plus x minus 4 equal to 0. So that means the function that I'm working with, f of x, is equal to x cubed plus x minus 4. And the derivative, f prime of x, is equal to 3x squared plus 1. So I'm going to start with my initial guess. Of course, we know that the formula for Newton's method says that, let's write this down for ourselves, x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. That is our formula. So I can say here that x sub 2 will be equal to x sub 1 minus f evaluated at x sub 1 divided by f prime evaluated at x sub 1. So this is equal to, we know that the first approximation here is given to me. That's equal to 1, so this will be 1 minus the original function evaluated at 1, so that will be 1 cubed plus 1 minus 4 divided by the derivative. 3 times 1 squared plus 1, evaluated at 1. All right, on your calculator, this is definitely a calculator problem. I get a value here of 3 over 2, which is equal to exactly 1.5. So my answer here is A. All right, problem number 12. It says that a particle moves vertically. Its height at a time t is given by h of t equals 2t cubed minus 7t plus 3, where t is measured in seconds and h is measured in feet. What is its acceleration when t is equal to 2? All right, so this height function that is given here, essentially this is a position function. We know the relationship between position, velocity, and acceleration is that velocity is the derivative of the position function, and acceleration is the derivative of the velocity function. So that means that the velocity function v of t will be equal to the derivative h prime of t, which in this case is equal to 6t squared minus 7. All right, so that means that the acceleration function, a of t, will be equal to v prime of t, or h double prime of t. This is equal to simply just 12t. So the acceleration then, evaluated at t equal to 2, is equal to 12 times 2, which is equal to 24. The units were given. This is feet per second squared. Answer here is E. All right, any questions that anybody would like to go back to on part 2? Number 11, yes. So usually we draw this little table for you guys. I didn't even bother with a little table because it's just one iteration. But if you just want to use your calculator, again, go ahead and save 1 in your calculator as A. Calculate the original function evaluated at A, save that as B. Calculate the derivative evaluated at A, save that as C. And execute A minus B over C. Yes? Number 8. I'll go back to it in a second. You good? Okay, which part did you not like? Over here? I plugged it into my calculator, so let's see, 1 cubed plus 1. So 1 plus 1 is 2 minus, so it's negative 2 over 4. All right, so we are on to the free response part. So a little bit of advice for you guys. That one? What was your question? I can't hear what you said. I mean, I want to say I guess you can. I've just never thought about doing it that way. Yeah, I guess you could. Yeah, I guess you could. Did you get the same answer? Yeah, I guess you could. Yeah. I don't see any reason why not. All right, so on the free response problems, on the multiple choice problems. And I know I'm talking to the possible third of the class who bothered to come to the review session, so you guys know this already. All right, so problem number 1 says we would like to answer the questions below based on the following information about the function f. And they give me the following information, that the domain of f is all real except x equal to -1. So x equal to -1 cannot be plugged into this function. X equal to -1 is a vertical asymptote. All right, good, noted. Next up, the limit as x approaches negative infinity of f of x is equal to 0. So I want you guys to kind of imagine, what does this look like? The limit as x approaches negative infinity of this function is equal to 0. So what does the left-hand tail look like? It sort of converges with the x-axis, right? The left-hand tail of this graph. And if it converges with the x-axis, that forms essentially an asymptote, right? So the x-axis becomes an asymptote here. All right, we know the following. These are sort of just some standard values that we're going to plot. F of 0 is equal to 0. F of 1 is equal to 0. F of 2 is equal to -1. And then they give me the following. All right, so the first derivative is positive on the intervals negative infinity to -1, and again from -1 to 2, and from 2 to infinity. All right, so this seems kind of odd, right? So on the interval from negative infinity to -1, and then from -1 to 1/2. So that means it's not a continuous interval. It's a -1 is not included in this interval, right? So we need to note that also. So this is where my original function, the original function f of x, will be increasing, as on these intervals. So go ahead and note this. This is intervals. These are the intervals of increase, all right? For f of x, for the original function f of x. All right, we know that f prime of x is negative, less than 0, on the interval 1/2 to 2. So this is the interval of decrease. That's where my original function f of x is going to decrease. All right? We also know that f double prime is going to be positive. AE, the original function, is concave up on the interval x less than -1 and x greater to +1. So I'm just going to go ahead and say concave up on this interval, and then between x -1 to 1, the second derivative is negative, so my original function is concave down on that interval. All right. Question number A here says, are there any horizontal asymptotes, and if so, where are they? Or what are they? Well, so we just talked about this limit right here. This limit, x going to negative infinity of f of x is equal to 0. That is an asymptote. So my answer here will be yes. And that is the line y equals 0, or the x-axis. And this is due to the fact, you don't have to write this down on the exam, but just to explain this to yourself, this is due to the fact that the limit as x approaches negative infinity of f of x is equal to 0. All right. Part B, are there any inflection points? And if so, what are their x coordinates? All right, so you can come down here and we can say that f double prime of x is positive for all x that's less than negative 1 and greater than positive 1, and it is negative for all x between negative and positive 1. Those two values form my inflection points, and they are inflection points because not only is the second derivative going to be 0 at those points, they actually change concavity. So yes, x equal to negative 1 and x equal to 1 are my inflection points. What are, in part C, what are the x coordinates of any local relative maxima? Okay, so a local max. All right, so let's come over here to the first derivative again. So I can see that from negative infinity to negative 1, first derivative is positive. Do you think negative 1 is going to form a critical point? Or a relative maxima or minima? No, because on the interval from negative 1 to 1/2, the first derivative is also positive. So I'm increasing on this interval, and then I continue to increase on this interval. So at negative 1, no, it's not a local max. But I continue to increase until I get to 1/2, and then on the interval from 1/2 to 2, the first derivative is negative, i.e. my function starts decreasing. So I increased until I got to 1/2, and then at 1/2 I start decreasing. So this means that 1/2 is a local maximum point, right? Yes, so there is a local maxima at x equal to 1/2. And then in part D, they ask me to go ahead and sketch the graph of the function. So what I'm going to do here is I'm going to start by plotting the points that were given. So first, the first point that was given, let's see, f of 0 is equal to 0. That point right there. F of 1 is equal to 0. And f of 2 is equal to negative 1. So those are some points that my graph is going to pass through. The other thing that I know is that I have a asymptote. The line x equal to negative 1 is an asymptote. Plot that with a different color. All right, so that pink dotted line, that is an asymptote. So I'm not going to cross that line. All right, so we have the following. We know that on the interval, again, let me scoot this down. On the interval from negative infinity to negative 1, the first derivative is positive. Therefore, my function is increasing. So how are you going to draw an increasing function over here on these values for x? The function has to increase, but also the left-hand tail of this function is going to converge to the x-axis. So that means here's the left-hand side of the tail, and we increase as we approach this asymptote, right? So it has to look like this. All right, so there's that left-hand side. All right, so I also know this. I know that the first derivative is positive on the interval from negative 1 to 1/2. So from negative 1 to 1/2, to this point right here, let me find a different color, to 1/2, here's 1/2. So on this interval from here to here, my function is going to increase, all right? And then it's going to decrease on this interval. So these are my intervals of increase and decrease, right? Let me make this dotted line all the way up here. It is going to increase plus, decrease minus, and then increase again. Increase, decrease, increase. All right? So that means we're going to look like this. We're going to increase, decrease, and then increase. That second derivative told me that those are the intervals of increase and decrease. And it almost sort of follows automatically then. You can check just to be sure right here at the end. Your intervals of concavity. We know that this function is going to be concave up for all x, let's see, for x less than negative 1. So this interval has to be concave up. And also for all x greater than 1. So starting here at 1, 1 is an inflection point. So from here onward, I'm concave up. And from negative 1 to 1, I'm concave down. Yes, that checks out. All right, questions? All right, number 2 says that the product of two positive numbers is 384. Let x denote the first number and y denote the second number. Use calculus to find the values of x and y that minimizes the sum of twice the first number plus 3 times the second number. All right, so the problem starts by giving me a constraint equation. It tells me that these two numbers, x and y, the product of these two numbers is 384. So my constraint equation says x times y is equal to 384. All right? The objective equation, the equation that we would like to optimize, it says find the values of x and y that minimizes the sum of twice the first number plus 3 times the second number. So the sum that they're describing to me is equal to 2 times the first number, 2x, plus 3 times the second number, plus 3y. I would like to optimize this equation, but right now it's an equation in terms of two different variables. So we can use our constraint equation, and you can solve for either one here. I'm going to solve for y. Y is equal to 384 divided by x, and I'm going to plug this y in for this y over here. So the sum is equal to 2x plus 3 times, well, y is equal to 384 divided by x. And what I have done right now is I've created a sum formula with respect to x. I have only one variable, which means I'm now allowed to go ahead and take my derivative. Before I take the derivative, let me clean up just a little bit. I like to clean up my algebra before I do my calculus. This will be 2x plus 1152 divided by x. All right, I would like to optimize this equation. That means I'm going to take a derivative, set it equal to 0. S prime of x is equal to 2. Let's see, 1152 is a coefficient that we're going to hold over. Hold on to that guy on the side for just a little bit. What is the derivative of 1 over x? Negative 1 over x squared. Again, just carry your coefficient. And we're going to set this derivative equal to 0. All right, so this means I have 2 equal to 1152 divided by x squared. I'm going to multiply both sides by x squared and divide both sides by 2. So x squared is equal to 1152 over 2, which is equal to 576. So that means x is equal to, and typically we would say plus or minus the square root, but the problem did say that the two values are both positive, so we don't bother with that. So this is just the positive part of the square root of 576, which is equal to 24. All right, so if x is equal to 24, remember I have a formula for y over here. Y is equal to 384 divided by x, but x is equal to 24. So I get that y is equal to 16. And now, because this is the free response part, this is part 3 of the exam, I'm going to do everything in my power to impress the person who is grading my paper. I'm not going to leave it right there. I'm going to report my answer very nicely and say x is equal to 24, y is equal to 16, and I'm going to block my final answer. Let me zoom out just a little bit so you can see all of my work. Questions? let's see, problem number 3 provides me with this graph. This looks like a piecewise function that they're providing me with, and we're being asked some questions that relate to the limits. So we can see that this function has two discontinuities, right here at -1 and also at 0. The first thing that the problem asks, did I really, my problem got cut off a little bit because I tried to blow it up. All right, number A here says, find the limit as x approaches -1 from the right-hand side of f of x. All right, so we're approaching -1 from the right-hand side. So here's -1, right? Here's a dotted line. This is x equal to -1. And I'm coming towards this dotted line, but I'm coming from the right-hand side. So as I'm approaching -1, closer and closer and closer I get, what is my y value here? +1, right? All right, part B says find the limit. Part B wants to know, find the limit as I approach -1 from the left-hand side. So this means I'm coming from this direction, and I'm heading towards the pink dotted line. What is the y value that I'm arriving at right here? -1. So the very next question then says, all right, the limit from the left, the limit from the right is equal to 1. The limit from the left is equal to -1. What is the general limit as x approaches -1 of f of x? Does not exist. So D and E. It does not exist because the limit from the left does not equal the limit from the right. D and E. All right, so part D says, let's find the limit as x approaches 0 of f of x. So as I'm approaching 0 from the left-hand side, if I come, I'm approaching a y value of 2. From the right-hand side, I'm approaching a y value of 2. So the fact is, no, I never meet. There is a discontinuity, but the limit from the left and the limit from the right, at least, are on their way to the same point, right? So the limit does exist, and the limit is equal to 2. So the limit is equal to 2. That's for continuity. So the definition of continuity would be that the limit exists, the function is defined, and those two things are equal. But for the limit to exist, the only criteria is that the limit from the left and the limit from the right are on their way to the same point. So it doesn't matter, even if that function is defined elsewhere, as long as the two limits approach each other. The limit does exist. All right, so part E, I'll just write it over here for you guys. In part E asks us to find f of 0. So what is the function value when I plug in 0? It's equal to exactly 1, right? And then finally, part F says, for what values of x is f discontinuous? For what values of x is the function f discontinuous? Well, I see two discontinuities. So remember, the definition of continuity is that the limit exists, the function is defined, and that those two things are equal. So right here, the limit exists, the function is defined, but they're not equal. So it's not continuous at x equal to 0. And over here, at x equal to -1, the limit doesn't even exist. So I failed the first property for continuity. So x equal to -1. Alright, so problem number 4 is a little bit of a curveball, but it's not bad if you just hold on a second and kind of just give it a chance here. So the problem says the following. A car leaves an intersection traveling east. Alright, so this would be x, right? So we start here at this intersection right here, and we travel east. We travel in this direction. Its position, measured in feet at a time t seconds, is given by x is equal to, so I'm going to write this down, x is equal to t squared plus 3t. At the same time, another car leaves the same intersection and travels north. So that must be y, right? This guy's traveling north. Its position, again measured in feet, at time t seconds is given by y equals 12t. Y is equal to 12t. How fast is the distance between the two cars changing when t is equal to 2 seconds? All right, so since x and y are both given, can we find the derivatives here? Can you tell me what is dx dt going to be equal to? 2t plus 3, right? How about dy dt? Dy dt is equal to simply 12. So the question here is going to be, what is dz dt? Okay? So a couple things that I need to find first. First of all, this is a right triangle, so I know that z squared is equal to x squared plus y squared. So from this, it follows the following. I know that z is equal to the square root of x squared plus y squared. And so z is equal to x squared plus y squared, so this will be t squared plus 3t, quantity squared, and y was equal to 12t, right? 12t, quantity squared. You can clean that up if you want to. I'm just going to leave that right there for the time being. All right, now, my job is to find dz dt. So here we go. Again, I know that z squared is equal to x squared plus y squared. So the derivative here will be 2z times dz dt equals 2x times dx dt plus 2y times dy dt. If you want to, really early on in the problem, you can go ahead and say, let's divide both sides by 2. If you divide both sides by 2, all the 2's are gone, right? So dz dt then is equal to dz dt is equal to x times dx dt plus y times dy dt divided by z. So as a function of t, dz dt will be equal to, remember, x is equal to t squared plus 3t. Dx dt is equal to 2t plus 3 plus y is equal to 12t and dy dt is equal to 12 divided by z is equal to the square root of t squared plus 3t quantity squared plus 12t quantity squared. All right, so there's dz dt as a function of t. So now finally the problem says, can you find dz dt when t is equal to 2? So that just means we need to plug 2 in here. All right, so here we go. Yes, I can do that. dz dt is equal to 2 squared plus 3 times 2, 2 times 2 plus 3, plus 12 times 2 times 12, divided by 2 squared plus 3 times 2, quantity squared, plus 12 times 2, quantity squared. I would say go ahead and use your calculator. All right, stick this on your calculator. So yes, it's a bit hairy, but it's okay. Just be methodical. Plug this into your calculator. I get a value here, double check me, of 179 divided by 13, which equals approximately 13.769 feet per second. right, questions for me? Yes. So I think in this problem, if I'm not mistaken, they did not indicate how many places to round to. Let me see in this exam. So when in doubt, go back to the general instructions. The general instructions of this exam also did not indicate what to round to. So again, our rule of thumb is you're always safe leaving an answer in exact form. So if you leave your answer in the form 179/13, perfect, you got credit. If the problem did not say what to round to, a safe place always then, or sort of our default, then is round to 3 decimal places. So we would have accepted either one of these answers. If the problem did not say what to round to, I imagine that the grading committee would be very flexible. If you gave more than 3 decimal places, that probably would have been safe also. But I would say our default is, if the problem does not indicate, round to 3 decimal places. All right, one more problem here. Number 5. Gives us a graph of the derivative of a function. So this is the graph right here. This is f prime of x. And we're being asked some questions. So in the first question, number A here, says for what values of x, if any, is the original function f increasing? Okay, so I'm going to remind you guys that for the function, original function f, where does f increase? F increases where the first derivative, f prime, is positive, right? So where is the first derivative positive? Where is f prime greater than 0? It is greater than 0 from -3 to -1 and from 1 to infinity. So those are the intervals of increase. So from -3 to -1 united with 1 to infinity. So my original function is increasing on these intervals. Number B says for what values of x, if any, is f concave down? All right, so if the original function f is concave down, so we know concavity deals with the second derivative, right? So that means that the second derivative is negative. And when the second derivative is negative, what does that tell me about the first derivative? The first derivative is decreasing. All right, so we have the graph of the first derivative. Where is this guy decreasing? Well, we're decreasing on the interval from -2 to 0. And that looks like it, right? So -2 to 0. That's where we are decreasing. All right, and then finally, the last question here, number C, says sketch a graph of the second derivative, f double prime of x. And this right here just serves as an example of why you need to always read very carefully. Because when I worked this exam the first time, I was like, okay, we want to sketch the original function. No, we want to sketch the second derivative. We're switching gears here. All right. All right, so you're provided here with this little coordinate axis that looks very much like, I'm going to zoom out so we can see both of these things on the same screen if we can. So this kind of looks, it's drawn to the same scale as the original graph. All right, so what's going on here is, so wherever the first derivative is increasing, so remember the second derivative is the first derivative to the first derivative. So if this guy is increasing, the second derivative is negative. Okay, so let's make some, so the critical points here are going to be the zeros over here. So the critical point here is -2. So I'm going to put a plus there. The first derivative is increasing, therefore this guy, the second derivative, is going to be positive on this interval. All right, so then on this interval from -2 to 2, let's see, no, we're decreasing from -2 to 0. We're decreasing, right? So this is, we're decreasing, so it's negative. And so I'm increasing here, but there's kind of something funky. I don't really like this problem because this was really unclear. What would you guys say? Does this thing appear to continue to increase, or does he level out? See, it's very, very hard to tell. I mean, it appears... I didn't write this exam. I wouldn't have made anything this confusing. So let's assume that it continues to increase. And if you look really closely, if you squint, it seems that it continues to increase. So let's call 0 to infinity then an interval of increase, which means 0 to infinity. This guy's going to be positive. So I'm going to show you guys something in a second. So that means positive, negative, positive. Right? That's what the second derivative is going to look like. It's going to be above the x-axis here, below the x-axis here, above the x-axis here. So let's quickly look at this scenario. Let's say that they continue to draw, just so we cover all of our bases here. Let's say they continue to draw this graph, and they actually did a really nice job, and they made sure that you could see that this thing really does. So I'm going to use a little ruler. This thing does level out. Right? So he has his tail end that is constant. It's neither increasing nor decreasing. What would happen to the second derivative if that is the case? Let's do that in pink so we can show. If that is the case, what would this guy do? He would, starting at, let's say it's here, right here at 2.5, we would do this. And we would converge to the x-axis right here. So I would have a function value of 0 because the function above it was neither increasing nor decreasing. Its derivative is equal to 0. All right, questions for me?